Today we're going to talk about exploration of the Kit Drivetrain. So we're going to go through what the Kit Drivetrain is, but along and like how it all works together. But the bigger piece of this is that it's really just a model and like an example of a lot of the different things we use to design our mechanical parts for the robot. So there's a lot of different pieces and bits of it. This is also really useful as the kit drivetrain is used by a lot of teams. It's an option to come in the kit. Every single new team, so every single rookie team or new team is given this drivetrain. So you'll see it a lot. A lot of robots are built with it, and it works really, really well. And it kind of solves the problem of how do you make sure the robot's going to be able to move around the field without having to have a ton of prior knowledge on how to actually design one that's going to be robust and meet the design challenges pretty well. So it's not just going to fall apart on the field. We want to make sure everyone's able to continue to play their matches and at least be able to move around. So yeah, the goal of these slides is basically to answer what is the kit drivetrain, what does it do, and how does it do it. We tried to do, a lot of the times the words in this slideshow I'm going to try to use as if like basically people have no prior knowledge. So as much as I can, if there's something that I say or something that you don't understand, please ask, and I'll try to go over it, because the goal is to have like as everything in here should make sense as much as possible. I tried really hard to do that with this one. Okay, so this is what the kit drivetrain is, or has been for at least the last 2 or 3 years. I think we've been on this version. So this is the AM14U4. So this is the 4th version of the AM14U style of drivetrains. It's produced by a company called AndyMark. They're one of the vendors that specifically came up to start selling products for the first robotics competition. So there's multiple. We'll talk about a couple others in here as we look at some of the other parts. But they have a huge amount of different robot parts that are designed for the first robotics challenge and also for a few of the other robotics competitions. They get used in there too. And because this is the option that every team can get, like I said earlier, this is used a lot, and there's a lot of different configurations. We're going to largely be talking about how to build this configuration, which is called the long configuration. There's ways where you can like make these rails shorter, and you can make it wider, or you could make it square. There's different ways you can configure it, but the long one is by far the most common, and so that's the one we're going to go over today. So this is the full 3D CAD model of it, and then this is what the real drivetrain looks like. There are full build instructions that AndyMark provides on how to like actually assemble it. That's definitely not what this is about. We're not talking about how to assemble it. We're going to actually talk about like why and how they designed it to do what it does. So like what do each of the little parts do, not how to actually put it together. AndyMark does a really good job of that in their build instructions. There's a video and a manual for that. So if we ever get to the point of building it, don't try to go through this slideshow and build one. Make sure you refer back to their manual and their video on how to do all of that. Okay, so what does the kit drivetrain actually do? So the kit drivetrain allows any team to very quickly assemble a base of their robot that's going to allow them to drive around the field and move around very easily. You do need to add the control system to it. So the kit drivetrain doesn't include the main electronics. We kind of include the gearboxes here. That would be where the electronics control, but none of the rest of it's in here. So we've gone over electronics before in one of our other lessons. So we can go back and look at that at some point to figure out how they would kind of integrate together. But once you add the control system, the robot's able to drive forward, backward, turn left, turn right. And it does that because it has 2 groups of wheels. So it has a left group of wheels. It has these 3 wheels on the left side, and it has 3 wheels on the right side. So that makes this the front of the robot and this the rear of the robot. The way this robot turns is the same way that a lot of any of our skid steer robots turn. That's kind of what skid steer is what it's called sometimes. Sometimes you'll hear it as like differential drive. There's a lot of different names for it, but pretty much any time where you have when you have 2 sets of wheels on both sides of the robot, and those wheels can be independently controlled, so you can drive them either forwards or backwards independently of each other. They allow you to turn. So all 3 of these wheels on the left side are all turning together, so you can't control the direction of each individual wheel. You can only control this whole group at one time. Same with the right side. And then when we're able to change their speed and direction, we can make the robot spin. So we can make the robot spin to the right, like described in this diagram, by moving the left group forward and the right group backwards. And the whole thing will spin around a point somewhere in its center, and it'll rotate around. And then if we do the opposite, and we have the right group going forward and the left group going in reverse, it'll spin to the left. So that allows our robot to be steered when we have the drivers actually driving it with a gamepad or joysticks or however they're driving it. They're able to steer the robot, drive it forward and backwards, and allow it to largely just get around the field. And this is by far the default standard way to drive. There are more complicated drive systems that can be done, but with the kit, this is the way that most people are set up, and this is the way the majority of FRC robots drive around the field. Okay, the biggest part of the actual kit is the frame itself. So the frame's the main structure, and this is where not only do you get it to be able to drive around, this also gives you a base, so all the teams can build up the rest of their robots off of this. So you would connect other beams and metal and anything else, depending on what your robot design is, you connect them to this drive base and to this frame so that you can have the other parts of the robot, the intake or the elevator or the launcher, or whatever else is going to happen with that year's game, they all get mounted to the frame. The specific frame in a Kit Drivetrain is made from bent aluminum sheet metal. So these profiles start out as a flat design. So they are cut out from a big flat sheet of sheet metal, and then parts of them are bent and curved over to provide strength to those parts. And then when you attach them all together, when you attach like all 6 of these pieces together, you get a really strong frame that is relatively good at resisting twisting, that's resisting to bending. It's a pretty strong package when you have these attached sheet metal parts together. There are 6 parts. There's 2 of the end plates. So you have these end plates back here where the blue arrow is pointing. We have 2 inner rails. You can see these are a little bit different. They have these parts that kind of stick up. That's for the gearbox mounts, which we'll talk about in just a second. And then we have the outer plates, or the outer rails, that are just a little bit flatter and don't have that little stick-up part. There are a huge amount of holes in the inner and outer rails, and they all do serve some purpose. They're designed in for a reason into the rails. There's no just like extra holes or anything. They all have some idea of what they're supposed to be there for. You'll almost never use them all at the same time because they're designed for different configurations. Depending on how big you make the chassis, you can use different holes to make your wheels be closer or further apart. There's a lot of different reasons for the holes to exist, but they're all kind of there for either attaching items or mounting wheels or different gearboxes. There's a lot of different customizations you can do with this. So it is important when you actually are building it to pay attention to the manual and know exactly which hole you're using for the size and the instructions you're following at that time. For the long configuration, we do have to cut. So we have to cut the M plate shorter. There are a few different methods to do it. If you don't have power tools at the time, you can do it manually with a hacksaw. However, if we're in our lab, we could do it with the reciprocating saw, or we can do it with the horizontal bandsaw. There's a lot of ways that we could cut those metal parts. I'm not going to go into that too much tonight. The frame is held together in the kit of parts robot using nuts and bolts. So fasteners in general is the name we give to any of the parts that are holding the robot together. So if we're talking about fasteners, we mean nuts, bolts, rivets like we used in the rubber band car, sometimes zip ties. On occasion, fasteners are glue or other adhesives. Sometimes it's tape. just anything that we're using to stick two things together and secure it are the fasteners that we use on the robot. And there's a whole wide variety of them. Sometimes certain fasteners are better for certain applications than other, and you'll learn all about kind of when to pick which and which ones to use. The so the kit of parts robot uses nuts and bolts to stick through and connect the end plates to the inner and outer rails, which is bolt those up tight. They have on this page we can see exactly the bolt is what spirals in or has spirals externally around it. So those are known as threads. The larger portion is the head of the bolt. Sometimes you'll call a bolt screw. Depending on which kind of application you're in at the moment, bolt and screw can be interchangeable. Most of the time in FRC, if you say one or the other, no one's going to be mad about it. Most of the time we'll use bolts for something that also is connected to a nut, but at the same time the verb for it is to screw it in or screw it together. You can also use bolt it together. So you'll hear them interchangeably. There's sometimes a difference. It's not a big deal if you know what it is at the moment. Bolt, screw, it's probably fine for right now. The bolts on the kitted parts chassis have a hex on the inside. So these are internal hex screws. So you put an Allen wrench, like shown here, into the end of it. That's how you're able to turn it. This is also known as a hex key or an Allen key. So a lot of things have multiple names, and you kind of just have to figure out what somebody's referring to. Does not always have one name for each tool or part or anything. The nut is the much shorter part. It has spiral threads on the inside. So to use it, you hold the nut with the wrench on the outside, and the nuts that we normally use in robotics and the nuts that are used on the kit apart chassis are what are called lock nuts. So they have this little bit of plastic, which is a nylon on the inside here, and that stops the nut from loosening due to vibration. So if we just used a regular nut that didn't have this little bit of plastic, a lot of times our bolts and nuts would loosen up. They might even come completely apart. They might fall off onto the ground, and then whatever we were trying to secure is no longer fastened together. And your robot normally doesn't work as well when you have nuts and bolts falling out of it. So we always use lock nuts for the most part, whenever possible, just because they're going to give a much more secure connection while the robot's actually driving around, getting bumped, and there's a lot of vibration that happens on the robot. To secure them in place, pretty obvious. The nuts, the threads of both of them get turned together, and you can tighten them down to secure the frame together in this application. In the next part of the actual structure of the kit of parts drivetrain are what are called standoffs. So standoffs make it a lot harder to bend or twist the frame. So they basically add support in the middle of these rails, because without them, if you were to like push right here in the center, you could imagine that this would be relatively easy to like bend this piece of metal, maybe dent it in a little bit, and we want to keep this as straight as possible. Normally on any of the robot stuff we're building, we want to keep all of our things that are, if we mount something straight on it, we probably want to keep it straight the whole time. So we're going to do whatever we can to design it in a way that it's strong enough to withstand any of our expected impacts, where if another robot's coming in and hitting it, if somehow it gets pushed in, anything like that, we don't want it to bend. So these standoffs help with that. In the kit drivetrain, the standoffs are made from these kind of odd-shaped rods. They're actually called churros because they kind of look like the churro, like the dessert. That's the kind of shape they have. They're kind of like a petal shape, maybe. They're a hexagon that have these kind of cutouts in them. Each of the tubes crossing between the rails is a standoff. So in this picture, you can see like each one of these is its own standoff. Standoffs have bolts that are secured into each end. So a bolt like this is going to go through the plate and actually be threaded into this standoff directly. So in this case, there's not a nut. We actually will put threads into this the internal hole in the center of this rod. and we'll tighten it down that way. So then you can like put a wrench across this whole thing. So this this churro is the same shape as, or the same like dimension sort of as a 1/2 inch nut. So you can put a 1/2 inch wrench on it. You can put a socket or a wrench on this bolt, and you can thread it into the rod, and you do the one on each side, and now those plates are secured together again, and they're going to be much harder to bend or twist because they have that extra support of that material on the inside. Now we're starting to get into actually how this robot will drive. So that's kind of the main portion of what we consider the frame and kind of the structure. And now we're going to talk about how we actually have the robots drive. And so some of this will be somewhat obvious. We're like, yeah, of course a motor does a thing. But a lot of the little details that we're going to go over are super important and very different than anything else you may have used or worked on in the past. Maybe you had like RC cars or something. A lot of these details are going to be definitely different when we're using something as big as these FRC robots. The kit apart chassis, also again known as the AM1 4U4. So if this is there, or Kit Drivetrain, any of those, they're kind of interchangeable again. It has the ability to have 2 motors on each side. So you have 2 motors and 1 gearbox. So these black and kind of silver parts right here are 2 of the motors. So these are the motors that were really common in FRC for a long time. I think we're going to talk about that on the next slide. Electric motors spin when connected to electricity, and so this is how we have to control and get battery. We have to get the power from the battery to them somehow to make them go the speed we want, and make them actually go the direction we want. All of that stuff. The gearbox is super important here because it converts the motor's speed. Where the motors, if you just have them connected straight, if you like connected a motor straight to a wheel, that wheel would be spinning really, really fast. It would be spinning too fast for us to actually use it. So the gearbox converts that fast speed to a usable speed for the wheels. So we're going to lower the speed from the motor so that we're actually able to drive the robot around and it's actually going to be able to be controlled. It's going to be able to like push into other robots well, that sort of thing, which is what the gearbox is designed to do. Okay, so shafts and axles. So to be able to actually do any of this power transmission, so we can take the energy from the motor, have it spinning, we have to be able to transmit power from like one thing to another. And one of the ways we do this is with shafts and axles, sort of any of these longer cylindrical-ish so some of them are just straight cylinders or have part of them as cylinders. Other times we'll use Hex Shaft, where we have this hexagon profile. And it's basically anything where a spinning part is mounted to it is either a shaft or an axle. If you use one or the other, there's probably some version where the one definition is better than the other at different times. But if you say one or the other, you're going to be pretty okay. So pretty much anytime something is spinning, it's on a shaft or an axle most of the time, or whatever it is spinning on is acting as a shaft or an axle. Okay, so the motors that are kind of standard for the kitbot, there's actually ways to upgrade them if you want. There's a lot of things you can do in the kitbot to add upgrades or change or modify, but we're going to talk about like the standard default one for most of the day. This standard motor is called a CIM, C-I-M. It's pronounced CIM. It's a little bit weird. It's an acronym to the motor company that used to make it. I think it's Chippewa Industrial Motor. That's not important. Everyone just calls them CIMs. When electricity is sent to the motor, the output shaft spins very, very quickly. The motor's face right here, so this is the face of the motor, the front of the motor where the output shaft is sticking out of. This flat part is called the face. It has 2 mounting holes. So there's 2 places where we can thread bolts into so we can mount the motor to our robot. There are 2 other holes on an actual sim, not in the CAD version, but actually on here that you can't. They're just there to actually hold the motor together. So they almost look like bolt holes. They kind of look like they have bolts already in them when you're looking at a real one. But 2 of them will look empty, and those are the ones we actually use for mounting. The sim is relatively simple. It has an output shaft up here. The sort of main body of the motor is called the motor can because it looks like a can. And then it has a couple wires coming out the back. The motors are mounted to the gearbox. The gearbox in this case is known as a Tough Box Mini. So that's what this part is, or all these parts. It's a specific gearbox designed by AndyMark. A lot of times there's gearboxes made by a bunch of different companies. Teams can also design their own gearboxes. A gearbox is just kind of the generic term for an assembly of gears that do that speed reduction for our motors. So the gearbox uses gears to reduce the speed of the wheels powered by the motors. Like I said before, but this is a really key important part. If the wheels were connected directly to the motors, the wheels would spin very fast, but the robot wouldn't be able to drive around. It wouldn't be able to turn well. It wouldn't be able to push things. You also really wouldn't be able to control it depending on exactly how fast it was driving. It would be too fast. So we need to have that reduction to be able to increase how much the robot can kind of push things and how well it can turn and how drivable it actually is. Okay, we're going to look at the parts of the gearbox. So we have the gearbox housing. So this is actually a plastic part that AndyMark makes specifically for this gearbox. It has a bunch of internal holes and pockets, so it's designed to not use a lot of plastic but still be really strong. It also has to have all the mounting holes for like the motors, so the motors mount to this. It has some holes for the rest of the gearbox components to actually be assembled inside of it. And the way this one is specifically done is it matches up some of these specific holes to the cutouts on the inner frame rail. So they're designed very specifically to go together. So this gearbox doesn't really work without also having an inner frame. You couldn't just like take this off and without doing any modifications use it in another part of the robot. You would need to add another plate here that would like mimic what the inner frame is doing. So the gearbox has 4 holes that allow it to be bolted to the inside rail. So that's how it actually mounts to the rails. We have some more bolts here that are going to do that. And then the gearbox housing also has those holes for the motors to mount as well. Okay, so now we're getting more into the details, and this is where it starts getting more generic. So this is not only just for this kit of parts drivetrain, it is also for a whole lot of things that we do on the robot. We'll use gears in a lot of different subsystems and different parts of the robot. Whenever we have motors involved, there's often gears involved. So a gear is just a tooth of wheel that allows motion to be transferred from one shaft to another, right? So if you can imagine we had a shaft spinning inside of this gear and we had a shaft in this gear. When we spun one gear, the other gear would spin because all of these little teeth would be hitting each other kind of like paddles, and they'd be moving along and making sure that these two shafts always spun together. When two gears are properly interlocked, this is called meshed. And so when one gear is basically connected to another gear at the right spacing, so how far apart this shaft is from this shaft, there's a way we can calculate exactly what that spacing is supposed to be, and we'll get into that in the future. And that lets us know that they're going to be meshed properly so that the teeth kind of hit each other in exactly the right spots. Because you can imagine very quickly if that distance is incorrect, if it's too far apart, they're not going to do anything because the teeth aren't going to hit each other. And if they're too close together, they're not going to be able to be mounted because the teeth would have to be like, the gears would have to be like inside of each other, which we can't do. Or they'd be like too close maybe and things would start jamming or it would just take too much force to turn. So we definitely want to make sure we get the right distance apart for the gears to make them work well and to get them to mesh properly so the gears are hitting each other in the right spot. The very basics of how gears work, and we'll have a couple more times when we go over this, especially when we start designing things, is that when a smaller gear turns a larger gear, the larger gear is going to turn slower than the smaller gear. So most of the time when we're designing anything, we want the smaller gear to be on the motor side, because the motors normally are spinning too fast, and so we want to make them spin slower. So we're going to have the larger gear be on the side that we're going to be towards our output. So in this case, like towards our wheel. So as this small gear is spinning very quickly, this slower gear will spin much slower, since there's a lot more teeth compared to the much fewer teeth on the small gear. A set of 2 gears that change the rotational speed, or pretty much any set of 2 gears that are meshed together, that sort of thing, are known as a gear stage. So this is a stage of gearing, or a gear stage, that is properly meshed together with a smaller gear and a larger gear, and it's going to be lowering the speed of the output. Okay, the gearbox that's actually in the Kit Drivetrain, that Tough Box Mini that we're looking at still right now, that's what it's called, has multiple gear stages. So there's a first stage and a second stage, and this allows us to reduce the speed even more in a smaller package. So if we had enough space, if we had like a much bigger thing, we could have this single gear on the motor, and we could put a really big gear right here, and we could get the same amount of reduction in speed. So we could get to like the same output speed with a single stage if we had a really big gear, but that ends up causing other problems when we have to worry about making sure we're not running things into the ground, and we want to make sure our wheel's at the right height. It's a lot of times when we're designing things where we have other constraints, not just how many gears we can use. So if we don't want to have to use a really big gear, we can add a second stage, and then we can connect them together. So this first stage is this blue small gear to the blue big gear, and then the small pink gear and the large blue gear are on the same shaft together. So every time the large blue gear spins once, the small pink gear spins once, and it's spinning this large second pink gear. Okay, so in this gearbox, so when we're talking about speeds here, we're talking about revolutions. We can do it in like revolutions per minute. Give me 1 second. Revolutions per minute, so like how many times this gear is spinning fully around in 1 minute. The green gears are spinning the fastest. They're connected directly to the motor. The yellow gears are spinning slower, and they're both spinning at the same speed. So this big yellow gear and the small yellow gear are spinning at the same speed, and they're spinning a little bit slower because we have that gear reduction from green to big yellow. And then the red gear, which is our output gear, we're going to actually like attach a wheel here shortly. It's the slowest one, since it's going from our medium speed yellow small gear to our slowest large red gear. So yeah, the big takeaway here is just like if you have 2 gears that are mounted kind of on the same shaft, they're always going to be spinning at the same speed, and then you can use that to get another reduction if you need to. Okay. The way we actually attach a gear to a motor, and specifically these sim motors, is the output shaft has a special little slot cut into it. That what can happen is this key, this little piece of metal right here, is able to press into this slot, and it'll stick up a little bit above the shaft. So we'll put a couple spacers first. So these spacers, they're just here to stop the gear from like rubbing against this non-moving part of the motor. So this back part of the motor right here doesn't actually spin. And so if this gear was pressed all the way up there and it was trying to spin really fast, you don't want that fast-moving thing rubbing against a non-moving thing. So these spacers are there to help prevent that, and they can slide and slip and spin a little bit easier against the non-moving thing than the gear can. The pinion gear, so that's this small gear right here. Pinion is normally a term we'll use anytime the gear is attached to the motor. And so any gear that are kind of designed to attach directly to a motor are normally called pinions or pinion gears. The pinion gear has the kind of opposite of this little slot cut into it. So it has a circle on the inside that can fit around the shaft, and then it has a little slot cut in to allow the key to slide into it. So as this shaft spins, the pinion gear has no choice but to spin with it. And so all the power from the motor can be transferred to the gear, and then eventually transferred to the gearbox and to the wheels. And on this motor assembly, the way we hold the gear on so that we can't just pull it back off is we have these little special retaining rings, and they have little tiny steel tabs in here that kind of fold out when we push it on, and then if you try to pull it off, they sort of dig into the metal and don't let it come off easily. So you can still get them off if you need to with like a screwdriver or pliers, and you can kind of get in there and pull it off if you pull really hard. But the gear itself, just in normal operation, isn't going to be able to slide off anymore like it would be without this little retaining ring. Okay, we do have another picture of the key. So the key, sometimes called a machine key, is really how we're going to transfer that motor power to the gear. So we made the pinion transparent so we can see through it. The key fits into the slot that is in the motor output shaft, like I said before, and there's also a slot in the pinion gear itself. It's actually a relatively common problem sometimes that someone will forget to actually insert the key. So you could assemble all the rest of these parts but not put the key in. And if you do that, as soon as you were to like hold the gear, this shaft would be able to just spin inside because there's nothing anymore attaching the gear to the rotation of the motor output shaft. So the key is super important to the whole concept of how this output works. Yeah, so with the key, the motor shaft and the pinion gear have to rotate at the exact same speed, and that's really what the key is doing and ensuring that these two are rotating together. Keys work pretty well to ensure that things are rotating together, but they're not the most convenient. You have to make sure you have the key, you have to insert it. Sometimes they can fall out or you can lose them. So they're useful and sometimes, but they're not the most convenient, especially across like a long shaft or anything. So instead, a lot of times we'll attach a gear to a shaft by using hex shafts and hex holes, sometimes called hex bores. And they're basically just a different way to ensure that the gear is going to rotate at the same speed as the shaft. So instead of having a round shaft that could just rotate inside of it without the key, the shaft is a hexagon and the hole inside the gear is also a hexagon. We have a few different standard sizes of these hexagons. So normally we're going to be using half-inch hex shaft and a half-inch hex hole. And that's measured from like one flat to the opposite flat across this hex shaft right here. We'll also sometimes have a 3/8 inch hex shaft, but for this drivetrain, we're only using half-inch hex. And we'll use hex in a lot of other places too. So it's not just here on the gearbox. We'll have hex holes inside wheels, inside gears, inside other power transmission objects. Anytime we need stuff to rotate in different ways or at different points, a lot of times we'll use hex to do that. It's a very convenient way to do it. Okay, so one of the other parts and one of the really crucial parts of the gearbox, and really a crucial part of any rotating system on our robot. So if we're building a drivetrain, or if we're building an intake, or a launcher that has to spin a wheel really fast to launch a ball out, pretty much anything on the robot that's going to be spinning with a motor, we have to do something to help reduce the friction and the rubbing that happens if you were to just spin something directly against a flat surface. The best way to do that is to use bearings. Bearings are specifically designed to allow shafts to spin very smoothly. So there's actually bearings inside of every motor. So there's motors use bearings to allow their shaft to spin really smoothly. And they're inside most of the parts on anything on our robot that's going to be spinning, especially things that are spinning quickly. They'll all have bearings. They are specifically designed to reduce friction. So instead of just having the shaft rub against the side of whatever the hole is, and then you'd have to worry a lot about like what materials they were designed out of, because you have different materials rubbing against each other. You create a lot of friction, which creates a lot of heat, and it just wastes a lot of the power that we're getting from our battery. So to not do that, the bearings have balls on the inside. So that's what these blue objects here are. So there's little balls inside of the bearing. So this is actually sometimes called a ball bearing as well. And they're running on a little track. Actually, two little tracks. So there's an inner race and an outer race. And the bearings are all able to spin freely inside of there. So these are the same type of bearings that if you played with like fidget toy or fidget spinners a couple years ago, or if you still have one sitting around, there are bearings in there. There's bearings in like skateboards. There's bearings on your bikes. There's bearings in your car. Anytime you have anything that's spinning relatively fast and you need to spin smoothly, ball bearings are normally used. The inner race spins most of the time. So if we have a shaft going through this bearing, most of the time the way they're designed is that the inner race is going to be, or the way that our mechanisms are designed, the inner race is going to spin with the shaft, and then the outer race is going to be held stationary. It's going to be like pressed into a part or held in a gearbox or something, and so it's not going to spin at all. And this inner race can spin, and then the balls can spin around and rotate inside of it too to have very little friction. So we'll use bearings a lot, and when we start doing more of our own designs in CAD and things, you'll have bearings that you'll have to put in places and make sure that they're all the correct bearings. These are just parts we purchase. We're almost never going to build our own bearings. These are just things we buy, and they do their job really, really well. And without them, robots would be very, very hard to would not work nearly as well as they do. There is a feature on some bearings, which is called a flange. And so the bearing flange is basically just this raised lip on the outside of some bearings. So some bearings don't have it, so you'll just have a normal bearing. And then in this case, you'll have a flanged bearing. The flanged bearing is just a feature that helps with how you assemble and how you can hold parts together. So the flanged bearing make it so that you can't have a part go all the way through a plate. So if we just had one of these normal bearings in one of the holes in the frame rail, we would just be able to stick it all the way through, and that's normally not good because we don't have anything like retain it to hold it in its exact place. Where with the flange, we can make sure that if we stick it through this direction, it can't get pushed out anymore this way. So if we add something back here, we can make sure that it can't be pulled back or pushed back, and it's going to stay in its spot. It is definitely very important to know which side of the plate the flange is on. So this is one of the things that's going to happen either when you're building this, or if we're building pretty much anything else on our robot. If the bearing has a flange, there is almost always a right way and a wrong way to put it in the whatever part it's going in. So knowing which way the flange goes is really important. If you don't, it's very likely that the whole thing could just like fall apart when you start running it. For the Kit Drivetrain, all the flanges are inserted from the inside of the robot. So they push in through the inside of the inner plate and the inside of the outer plate. That's just how it's designed. You could design a version where they're all inserted from the other way. You just have to do other things in your design to ensure that the bearings aren't able to fall out. So that's why it's really important to know which way, because normally they're going to be designed for one way or the other. And one way works, the other way almost always fails. Okay, so there's a host of different bearings that are actually included in the kitbot. And there's a variety of different kind of dimensions that we can talk about when we're talking about bearings. So not every bearing is going to work in every application. They all have different specifications. So each bearing has a outside size, which is known as the outer diameter, or sometimes abbreviated to OD. So that's how big this outer race of the bearing is. So basically like what hole the bearing will fit into. You You can also have different inside sizes. So the inner diameter, or ID. So that's how big the opening inside the inner race is. So what type of shaft can fit through it is the inner diameter. Just like shafts, and a lot of times in FRC, we'll either have round bearings like we see here, where we have just a round circle, or sometimes you'll have hex bearings. So in here, we have an actual hexagon kind of socket that's cut out so that a hex shaft can fit through it. And then on all of these bearings, and on most of the bearings we're going to use in FRC, sometimes it'll be a little bit different, but most of these, they're going to have this gold piece of metal, or this gold yellowish piece of metal. And these are called shields. And their job is just to protect the balls that are behind them. So they have all these balls running and spinning around behind them. We want to make sure that we don't get a bunch of dirt or debris or damage going on inside there, that are going to make it so the balls can't spin freely. So these shields protect the balls from any sort of dirt or anything else that's going to make it so where the bearing doesn't spin as nicely and gets damaged in some way. Okay. Anytime we're designing shafts and axles or anything like that, we always have to figure out how they're going to be held into the robot. So we have to figure out what we're going to do to what's called retain them. So we have shaft retention or retaining methods for the shafts. One of the ways we can do that is by modifying the ends of the shafts. And there's a bunch of different ways where we can modify the ends of the shafts, and a lot of times this is a lot of what we'll end up using our lathe for, is doing modifying the ends of the shafts to allow us to retain them in place somehow, so the shafts can't just slide back and forth. So in the case of this Kitbot drivetrain, one of the shafts is modified so that it has a 3/8 hex in the middle. So this started as a 3/8 hex shaft. So all of it was 3/8 hex. And then they went through and they modified it so that the ends of the shaft were turned to a round. So these are 3/8 round shafts on the end. And the reason for this is because if we put a 3/8 round bearing on both sides of this small shaft, now this hexagon part can't slide back and forth anywhere, right? So this thing can still spin really freely, which is great. But if you try to like push or pull this, it's not going to be able to do it. Because the little bit of the hex that's still sticking up, that's a little bit bigger than the 3/8 circle, can't fit through the bearings. So this is definitely one way to retain a shaft, is basically to have a hex shaft in the middle and then a round shaft on the ends, and then it can't slide back and forth. Another way to retain a shaft, or to retain parts even on the middle or in the middle of the shaft, is what's called an Eclip. So this blue item right here, this is a little piece of metal that has this kind of specific shape. I don't exactly know why it's called an E. Maybe it sort of looks like an E in some weird world. But that's what they're called. They're called Eclips. And in this specific case, it's used on this shaft to stop the larger gear from the second stage from being able to slide around too much. So it holds it up towards the front of the gearbox and stops it from being able to slide backwards. There is actually a specific groove made in this shaft called a E-clip groove. Sometimes you can kind of interchange it with a snap ring groove. That's another type of kind of small ring that'll fit into a groove. And they have specific dimensions for each type of clip that's going to be pushed in there to make sure it can slide in and it's not going to just fall out, right? Because you can imagine if you made this groove too deep and you made like it was too small, this wouldn't like snap over onto it properly, and it could just fall out. So you have to make sure you get it all to the right dimensions. But then this E-clip can just be pushed on, and the little sides of the metal will open up, and it'll go around that shaft and just kind of grab it, and then it stops the gear from sliding back and forth. We've already mentioned this a few times, but we make sure we can see it. So the output shaft of the gearbox is a hex shaft. So that's what this green shaft is. And so the bearing here is a hex bearing. So it allows that hex shaft to go all the way through it. And then the output on the end over here is also a hex bearing. So that's just easier, so you can use the same bearings on both ends, so you didn't have to like modify this end at all. This just makes things a little bit simpler for this whole process. Okay, so that's mostly how the gearbox works. Now we're going to look into what the wheels and how we actually power all the wheels on the Kit Drivetrain. So the kit uses the specific AndyMark high grip wheels. That's the name of them. They're specifically designed for FRC robots. They have this like tread pattern cut into them to kind of grip the carpet pretty well that we use in FRC. And each wheel has a hole pattern. So there's like a circular pattern of holes going around this larger hole. And this pattern allows us to bolt different things to the wheel. So we can bolt into this wheel if we want to mount various ways to actually power the wheel and make it turn. The Kit Drivetrain has 6 wheels, 3 on each side, which we already saw. Some of them are set up a little bit differently, but basically the center wheels on each side are set up differently because they're getting mounted directly to the output of those gearboxes. And the corner wheels in all 4 corners of the robot are pretty similar setups since they don't get mounted directly to the gearbox. So we'll look at both of those 2 types of wheel assemblies here in the next couple slides. The center wheel assembly are spun directly from that gearbox. So they're actually mounted to that center output hex shaft. And like we said before, if we want anything to spin directly to a hex shaft, you have to have a hex bore. So we'll have this hub right here, which I think we're going to see in just the next page. But that's actually allows the hex shaft to go into it. And then as the hex shaft spins, the whole hub spins, and it's bolted into these pulleys and the wheel, and so this whole assembly is going to spin. And we'll talk about what each of these parts are here shortly. These wheels also have parts bolted onto them that are going to allow us to spin the corner wheels too. So all 6 wheels of this robot are actually driven. So the motor is turning all 6 wheels all the time. So none of the wheels are just acting like they're just not free spinning or anything like that. They're always being powered by the motors, which is really important in FRC. Any of the wheels that touch the ground, you almost always want them to be powered, or you potentially run the risk of getting like high centered or stuck on something. It's sort of like how if you have a car that you use to go like off-roading, you want to make sure it has all-wheel drive. In FRC, we almost always want all-wheel drive on all of our robots, just in case something happens, and it helps with pushing. It helps with a lot of things if we have all of our wheels powered. Okay, so this is specifically what the Hex Hub is. And a hub is basically just a part that allows a wheel or a mechanism to mount to a shaft. So it's going to have the sort of internal cutout for mounting to a shaft. So in this case, it's going to have a 1/2-inch hex socket that allows us to put a hex shaft through it. Then it's also going to have some features that allow us to mount other stuff to the hub. So in this case, it's going to have this bolt pattern that allows us to mount the wheel to the hub. So the center wheel allows us to mount to the output of our gear, or the center wheel hub allows us to mount to the output of the gearbox, thus spinning that whole center wheel assembly and getting power to the actual ground now. So as long as we have this and that wheel mounted to the gearbox, we could at least drive the robot. We wouldn't have power to the outside corner wheels yet, which we're going to go over how we do that in just the next few slides. So the other parts that are mounted to this center wheel assembly are pulleys. The center wheel assembly has 2. So there's a pulley on the front of the wheel and on the back of the wheel. There are 6 bolts that mount the pulleys and the hub to the wheel. A quick tip, pretty much anytime we're tightening up anything on our robots in FRC, if it has a lot of bolts, sometimes if they're in a circle or if they're in a square, in general, you almost never want to tighten the same side of the bolts at the beginning. You always want to like put in one bolt and then jump to the other side, tighten one bolt, jump to another side again, tighten a bolt, and kind of just spread it out as evenly as you can. What happens if you don't do that? So if instead of doing this pattern, I went ahead and I just like tightened red and then tightened green and then tightened orange. If you tighten those all down, the whole pulley might start leaning to this side. And then by the time you try to tighten these other three, you're not going to be able to adjust it. So then the whole thing's not really centered. It might not be level. It's just not going to be fit properly. So anytime you have the option, you pretty much always want to tighten one down or get it even just loosely tightened a little bit, and then jump to the other side, and then get the rest of them kind of tightened in a little bit, and then go back and fully tighten all of them once they're all kind of threaded in a little bit. And that'll help make sure it's seated correctly and tightened properly. Okay, so the pulleys work with a belt. And so this is a similar concept to sort of how gears work, except the belt allows us to transition or transmit power over a much bigger distance. If we were only using gears here, you can imagine we need to have like a lot of gears or two really big gears, and that's not going to make the design work very well. It's going to end up being a lot heavier. So it's not going to work as well as the belt and pulley system does. So the pulleys are also toothed wheels, so they have a similar profile. Like if you just looked at a cross section, if you like cut this in half and kind of looked in here, you would see little teeth very similar to a gear. Except the teeth here aren't designed to mesh to another pulley. So you can't just take two pulleys and kind of put them next to each other and make them act like gears. Like they might work a little bit depending on their design. These ones wouldn't because they have these like flanges on them, so the teeth would never meet. But they might work a little bit, but they're not going to be very efficient. They're not going to work very well. They're going to be really noisy. It's just not going to be great. Pulleys are designed to specifically work with belts. So the belts have kind of the opposite tooth pattern to these pulleys. So when the pulley spins, the belt's able to spin the exact same amount of times, or the exact same amount of distance, and this pulley over here will spin the same rate as the pulley on this side. And so that the big deal with pulleys and belts is that they allow us to transmit power over a much bigger distance than gears. They're also normally they can be made out of plastic. We can actually 3D print a lot of the pulleys we use, so they're super cheap and easy to make for us. Where gears are normally going to be made out of metal, either aluminum or steel. They're going to be heavier. And so they're not always the best choice. A lot of times, we really like using belts and pulleys when we can for a lot of different mechanisms on the robot, just because they're so much lighter and they work really well, especially if you have to go a big distance away from something. Okay, the corner wheel assemblies are relatively similar to the center wheel, but they're a little bit different. So each one of these only has one pulley, since we're only transmitting power from the center wheel to each of the outer wheels. We don't have to have another pulley to send a belt to somewhere else. And the corner wheels don't have a hex hub. So instead, they have two bearings that are actually mounted in the wheel. So there's a bearing right here. It's kind of that the sort of different gray color here, and then one here in the pulley. And so those bearings are really important because they allow this wheel to spin freely again, just like any bearing does, right? We're always using bearings to allow some rotary part to spin well. They spin on a bolt. So we have these really large bolts that we're going to use as an axle. So we're going to stick this bolt all the way through this frame, the whole corner wheel assembly, and this other rail. We'll put a nut on the back side of it and tighten it down so we can make sure this bolt doesn't come out. And then these bearings here allow the wheel to spin on the outside. So in this case, the inner race of the bearing is actually going to be kind of stationary and not spinning very fast, and the outer race is going to be spinning at the same speed as the wheel, and that's what's going to help us reduce friction and like make the whole component work. The last part that we're going to talk about, I believe, on these corner wheel assemblies are the spacers. So a lot of times on a shaft like this, or on any of the shafts, we need some way to make sure we're locating the wheel in the right spot kind of along this shaft. So if we didn't have the spacers here, this wheel could like slide side to side, and we don't really want that. So we use spacers, which are all kind of depicted in orange here, to fill up any extra space on our shafts or axles so that the wheels can't slide side to side. So this happens too with any of the gearboxes we make. We may need to make spacers. For making an intake or a launcher, anytime we have pretty much anything spinning on a shaft, a lot of times we'll need to make spacers to hold that thing in the correct position that we want it in. Okay, just about done. I think that was the last part of this. So the big takeaways from this presentation are this type of drivetrain, often called a differential drive or a skid steer or a tank drive sometimes. They change direction by changing the speeds of the wheels. So if one's going faster than the other, you're always turning. Or if they're going opposite directions, you're definitely turning. The gearbox converts the motor's fast speed to a usable speed for the wheels. We're going to do that a lot from pretty much every mechanism we design. We're going to have some motor with some way to reduce the motor's fast speed to a usable speed for that mechanism, whether it's an intake or an elevator or an arm, whatever we're building. This is almost something that almost happens in every single one of our mechanisms. The gears and pulleys are used to transfer that rotation, right? So we can use it to either transfer it over a distance. We can also use it to change the speed that something's spinning. So if you had the pulleys could work in the same way as gears. If we had different size pulleys, they would change how fast they're spinning. But since we had the same size pulley, they were the exact same size. We call that 1-to-1. We'll get into that a little bit more later. That lets them spin at the same speed. Bearings allow shafts to spin smoothly. They reduce the friction involved, so there's less heat generated, there's less noise. And so the shafts spin much nicer when you actually have bearings. A hub is a part that allows a wheel or mechanism to mount to a shaft. We're going to use hubs in a lot of different places on our mechanisms too, not just here. And then spacers and eclips and retaining rings, any of those types of things are used to hold items in position and are also used to make sure the shafts stay in position as well. So there's a lot of different, there's a few others that we'll go over too when we'll learn about later that are ways to hold items onto shafts or to hold the shaft in position. But those are a couple to get us introduced to the concept.